Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about independence between events. In order to define independence, we have to remember the definition of conditional probabilities. So imagine that we have a certain probability space and we want to condition on a certain event A. This is a Venn diagram of the probability space. Remember that in Venn diagrams, the whole probability space has area 1 because areas correspond to the probabilities of each of the events, and each event is represented by regions that are enclosed by a line. And within that probability space, we have this event A and B. Okay, these two events. And their probabilities, again, are given by their respective areas. Now, what we say is we want to condition on A. That means that we have this information, this additional information that the outcome is for sure going to be in A. So all of this stuff is just not going to happen. In order to account for that, what we do is we create a new sample space where the sample space is actually A. Okay, a new probability space, where the sample space is actually A. So that's why I need to blow up all of the areas by 1 over probability of A, so that the new sample space has probability 1. And then within that new probability space, if we're interested in the conditional probability that B occurs, well, now we know that, let me erase all of this stuff. Now we know that these outcomes that are outside of A cannot have occurred. So if B occurs, we have to be in here. That's why when we compute the conditional probability of B given A, we look at the probability of the intersection between A and B, and we have to divide it by the probability of A, because remember, we have to blow up all of these probabilities so that we have a valid probability measure within this new probability space. Okay, so hopefully this gave you like a quick idea, or it refreshed a little bit what conditional probabilities mean. At the end of the day, the conditional probability of B given A is the probability of the intersection divided by the probability of A. And what it means is, if we know that A happened, what's the probability that B also happened? All right, so after all of this, when are A and B independent? They're independent when the probability of B, which is the area of the circle here, is exactly the same as the area of this new region, which is the probability of the intersection blown up by the probability of A. If those two areas are the same, if those two probabilities are the same, then we say that the two events are independent, which makes a lot of sense, because this means that when we have incorporated this information that the outcome has to be in A, nothing has changed about B. Okay? We still have the same estimate for the probability of B. Okay, so two events are independent. Two events A and B are independent if the conditional probability of B given A is exactly the same as the probability of B. By the chain rule, we can write the probability of the intersection as the product of the probability of A times the conditional probability of B given A. If we plug in probability of B there because they're independent, we get this equivalent definition for independence, which is that the probability of the intersection is equal to the product of the individual probabilities. And we often use this definition instead, because when the probability of A, for example, is 0, then this probability is not, this condition is not well defined. Okay, so let's take a look at this example, which is from the video on estimating probabilities from data, where we were considering the voting patterns of politicians in the House of Representatives of the United States in 1984. And there were these two issues that we're interested in: duty-free exports and budget. This was budget is represented by an event B, and duty-free exports is represented by an event D. We used empirical probabilities to compute the probability of D. So that probability is just, we count how many times D happened. This is just a brief review on empirical probabilities. And we divide by the total number of votes. And if we are interested in the conditional, so That's 174 over 400, 0.43. I gave it away, but if we want to compute the conditional probability of D given B, we look at the, I hope I did this right. No, I did exactly the opposite, right? So it's good that I looked at this. So I explained to you how to get the probability of B. Okay, and I don't know why. So now, okay, maybe let's jump here. The probability of D, which is really what we're interested in. And I hope you caught that and you were thinking, okay, Carlos has just gone crazy, I guess. The probability of D is the number of yeses we have for duty-free exports divided by the total. And now we're going to compare that to the conditional probability given B equals yes. So we're only interested in these guys now, equals yes. And we look at how many of those, for how many of those D is equal to yes, okay? And now this is correct. We see that it's much more likely that a politician votes yes for duty-free exports if they have also voted yes for the budget. So knowing about the budget definitely changes the voting, the likelihood that they vote yes for duty-free exports. So these events are clearly not independent, according to our definition. But things can get tricky. So let's take a look at two other issues. Immigration, which we represent by an event I, and anti-satellite test ban, okay, which is represented by an event A. We do exactly the same thing. So probability of A, so how many of them voted yes for A out of the total, 0.566. Probability of I, how many of them voted yes for I out of the total, that's the probability of I. And now, what's the probability of the intersection? Maybe pause the video and think for it for just a moment. So we need to see how many of them voted yes. So how many outcomes are in A and in I, and those are these guys, divided by the total. And now to check if these events are maybe independent, we're going to compare this to the product of the probability of A and the product of the probability of A and the probability of I, according to our definition of independence. And the products are very similar. So I would say it looks like these events are independent. And now, especially if you're a math major, you'll be like, wait a minute. That's actually not true, because you gave us a definition. In the definition, it says that the probability of the intersection has to be exactly the same as the product, not approximately the same. And that is true because the definition occurs in the world of probability theory. We discussed a little bit the distinction between probability theory and statistics in the video on estimating probability from data. What happens when you encounter actual data is that things get very messy. In this case, the issue is that empirical probabilities are never exact. So stating that something is that two events are independent for sure is going to be extremely complicated. Okay, there is some machinery involving hypothesis testing or confidence intervals and so on to make statements about that. And statistics actually spends a lot of time, a lot of statistical theory and statistical techniques aim to be able to make statements of that sort, but it gets very, very complicated. For now, I just want you to be aware of that challenge. What we can definitely say here is that if we estimate the conditional probability of A given I, so that's the probability that someone votes yes on A given that they voted yes on I, so we look at these guys and we see how many of them voted yes, well, that conditional probability is very close to the probability of A, so we can actually state that actually the conditional probability is very close to the actual probability, which is what we care about at the end of the day. In order to illustrate further this challenge brought about by the fact that empirical probabilities are always just approximate, let's take a look at another example. Okay, we're going to study the relationship between Tom Brady winning the Super Bowl and there being a Category 5 hurricane in the North Atlantic Ocean. Category 5 hurricanes are the maximum category. Okay, so they're devastating natural disasters. So let's take a look at the data. So I have 20 years of data. And now we're going to estimate the probability that there's a hurricane, that's the event H, right? And the probability that there's a hurricane if Tom Brady wins the Super Bowl. Just apply empirical probabilities. If you want, you can pause the video and try to estimate these two quantities by yourself. It's really simple, right? So for hurricanes, we just count how many hurricanes are recorded, and they happen to be 8 out of 20 years. So the probability is 0.4. And now we want to see what's a conditional probability that there's a hurricane if Tom Brady wins the Super Bowl. So now we're only interested in years where Tom Brady wins the Super Bowl. There's 7 of them. And now we see out of those, when was there a hurricane? And we see that there were 4 hurricanes. So the conditional probability that there's a hurricane if Tom Brady wins the Super Bowl is higher. It's actually much higher. It's 0.571. So should we conclude that Tom Brady made a pact with the devil, which implies that, sure, you're going to win a lot of Super Bowls, but then there are going to be more Category 5 hurricanes in the North Atlantic? Probably not. Okay, so what's the issue here? The issue here is that this number is pretty small. If you're a football fan, that number is ridiculously large, ridiculously high, but it's just 7 data points. So the estimate for the empirical probability is actually quite unstable. To show that, let's imagine, I don't know why this is repeated here. Let's imagine that Tom Brady actually won in 2012. And again, if you're a football fan, and if I'm not mistaken, they were supposed to beat the Giants that year. So actually this almost happened. It was really, really close. And imagine also that in 2017, they had lost instead of winning. And if you're an Atlanta Falcons fan, I'm sorry for the extremely painful memories. But again, it was super, super close. This almost happened. So in that case, what happens to the probability of hurricane? It's exactly the same, right? We haven't changed anything here. The probability of hurricane is still going to be 0.4. What about the conditional probability of hurricane given Tom Brady winning? So now this has changed in our virtual reality where Atlanta Falcons, yeah. I always get confused between the Atlanta Hawks and the Atlanta Falcons. Anyways, Atlanta fans are not traumatized, they actually won that Super Bowl. Okay, so how many out of these 7 years, how many hurricanes do we observe? 1, 2, and 3, okay? And 3 over 7 is 0.43, which is as close as it gets to 0.4, given that we have to divide by 7, right? So it's very likely that in this case, these 2 events are for sure independent, right? Although, if you have some theory about why they could be dependent, I'm all ears. But, it seems that they should be independent. It's just that we don't have enough data, so the empirical probabilities are only approximate, and that's why they look like they might not be independent. Again, a very important challenge when we're considering independence is that empirical probabilities are usually approximate. All right, so we have been talking about 2 events up to now. Like, when are 2 events independent? What about 3 events? Well, when we consider 3 events, something kind of surprising happens. Imagine that the events A and B are independent, B and C are independent, and A and C are independent. Okay, so these events are pairwise independent. Does that mean that they're truly independent? If these 3 events were truly independent, we would think that the conditional probability of C given the intersection of A and B should be equal to the probability of C because, they're all independent. So the conditioning should not change things. So we'll see that this is actually not true. Pairwise independence is actually not enough to imply true independence. In order to see this, let's take a look at an example. We're going to build a very simple probability space where we have 2 fair coin flips. So the outcomes are heads, 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 tails, tails, heads, tails, tails. Okay? they're fair coin flips. So each of these outcomes, when we look at the event associated to the outcome, so the event that contains, for example, heads, heads, it's equal to 1/4. Same heads, tails, tails, heads, tails, tails. Okay, they all have the same probability. Okay, so now we're going to consider 3 events. The first event is the first flip is heads. The second event is the second flip is heads. And the third event is that the flips are the same. We either get heads, heads, or tails, tails. So let's take a look at, and this is, a useful exercise to just remind ourselves of how we're defining probability spaces and so on. Maybe you can pause the video and figure out what outcomes are in each of these events. Okay, so if you want, go ahead. If you don't want, let's continue. First flip is heads. Well, it's this event and this event, right? Second flip is heads. It's this event and this event. And the flips are the same. As I said, is either heads, heads, or tails, tails. All right, so those are the events that we are interested in. So now let's compute the probability of these events. What's the probability of having of the first coin flip being heads? Well, the event is the probability of the union between heads, heads, and heads, tails. These are disjoint events. They cannot happen at the same time. So we can just add the probabilities. We get 1/2. What about probability of B? Again, this is the union of these 2 disjoint events. We can just add 1/4 plus 1/4 equals 1/2. For C, it's heads, heads, or tails, tails. Again, disjoint events. We add 1/2. Okay, so far so good. Now let's take a look at the intersection. What's the intersection between A and B? The first coin flip being heads and the second coin flip being heads. Well, there's only one outcome in that intersection, right? It's heads, heads. So the probability of the intersection is 1/4. So this tells us immediately that A and B are independent, right? Because 1/4 is equal to 1/2 times 1/2. What's the intersection between A and C, which is first coin flip is heads and both coin flips are the same? Actually, it's the same event, right? Oh, this is just what I just said. Okay, so they are independent. So now let's go back to the intersection of A and C. Same intersection, also equal to 1/4, also equal to the product of the probabilities of the individual events. So A and C are actually also independent, which makes sense, right? You flip a coin. If I tell you that the first coin flip was heads, this doesn't, well, make sense. I mean, you have to think about it, but it doesn't actually give you information about whether the 2 coin flips are the same because you don't know the second coin flip. What about B and C? What's the intersection between the event, the second coin flip is heads and both coin flips are the same? It's exactly the same one again. Again, 1/4. Again, the product of the individual probabilities. So it turns out that B and C are also independent. Does this mean that A, B, and C are completely independent? We're going to, reason mathematically now, but now imagine that you know that A and B happened. If A and B happened, what's the only possibility? The only possibility is that we've had heads, heads. Is this informative about whether C happened? We know that C happened for sure, right? So it's very clear that the 3 events are not independent. Now let's take a look at this mathematically. It's always good to, try to reason about things intuitively, but then always check whether the math works out. So A, B, and C, we have established they're pairwise independent. If the 3 events are truly independent, then knowing A and B, knowing that both A and B happened should not affect the probability that C happened. So let's take a look. What's the probability of C given A and B? By definition, and this might be a little bit tricky if you don't remember that, you can just consider that this is the intersection of A and B, so it's an event. You can call that event D if that is helpful. By definition, it's the probability of the intersection between C and that event, which is the intersection of all of them, divided by the probability of that event, which is the intersection of A and B. Okay, so what is the intersection of A, B, and C? Well, if A, B, and C happen, then there's just one outcome that is inside that intersection. That's heads, heads, right? So the probability is, I don't know how I've written it here. Yeah, that's heads, heads. And now what's the intersection of A and B? It's also heads, heads. So what is this probability going to be equal to? It's a probability, it's 1, which is exactly what I said intuitively. It's different from the probability of C. So C, A, B, and C are not truly independent. In order to capture this, we say that N events are mutually independent if they are truly independent, which means that all of these conditional probabilities are the same as the probability of the event. And in order to guarantee that, we need a stronger condition than pairwise independent. We need for any subset of M of these guys, for M smaller or equal to N, we need that the probability of the intersection is equal to the product of the individual probabilities. We need this to happen for any subset, not only for the N of them, okay? And then this is going to guarantee that any conditional probability of AI for any of the AIs is equal to the probability of AI. So to see why, let's take a look at our example. We would have that we're interested in the probability of A3, which in our case was C, conditioned on both A1 and A2. This is the definition of this conditional probability. And now, if this condition holds, then both the probability in the numerator and in the denominator factorizes into the individual probabilities. And now we can just cancel them out. And we end up with the probability of A3. So what we said was a reasonable kind of definition for what true independence should imply actually holds under this definition of mutual independence for multiple events. All right. So what have we learned? We have defined independence, and we have shown that pairwise independence does not imply mutual independence. And I would also argue that we have encountered a fundamental challenge in data science, which is that empirical probabilities are never exact. So when you take definitions that come just from probability theory and you apply them in situations where the probabilities are estimated from data, you have to put your statistical thinking cap on and take into account that the empirical probabilities are going to be inexact. And that's all I got. Thank you very much.